about shear stress and force concept. Okay, shear stress itself, as we have said, is force over area. So what is shear force? Shear force is just this force over here. So it is nothing much. Okay, and then when you're dealing with this type of questions, okay, when you're dealing with this type of questions, okay, when you have a certain plate, then when you move this plate, um what is the forces and what are the viscosity of the thing. So what is the shear stress and shear force now? Okay, so apparently we have to make certain assumptions before we apply, because this is the question, but there is certain assumption when we are dealing with all these things. Okay, so give me a minute. So the assumption wise, for there's a three rule. Okay, the first rule is that we assume that no slip is between the fluid and the plate. So what does this mean by no slip? Because I don't know, so I go and search. So no slip condition means that assume that the molecules of the fluid stuck to the surface of the plate itself. So what it means is that imagine you have this um maybe you give me a minute. Okay, I found a picture. So no slip wise is that at this point the velocity should be 0 compared to here. And then for if it's slip, right, it is somewhere here, which is outside of the internal pipe, which somewhat says that there is a certain um, fluid pressure that kind of push of the solid, that kind of push the solid surface. So in a certain sense, you can say that no slip is in at here. So for my notes itself, it says that assume no slip between fluid and plate surfaces. So apparently, the plate itself is not consider any form of friction, so it didn't cause any form of slipping, I think. Yeah. So you can just take this as a rubbish. I don't know what I'm saying, but I just realized that this is the from my picture itself. Uh, hold on, where's the damn it thing? Hold on. Yeah, I give up. Okay, you just go and find yourself if free. Okay, the next rule is that, so you just need to know the first rule is that the velocity ends at this portion here. Okay, if it's not, if it's no slip, then it's a more complicated stuff. So we assume that it ends in here. Okay, I mean the velocity at here is 0 compared to here. Okay, and then the second assumption is that no pressure gradient, meaning if you know that there is a water tank over here, the pressure at here compared to the pressure at here is kind of lower, right? So we assume that there is no such thing at all, because if you were to take a look in all these questions, we are dealing with all our pipes and small distances. Maybe which is which is less than 1 meter lah, okay, which is somewhat 0.05 meter, which is very small. So the pressure gradient that is is actually negligible. And yeah, unless you're studying big stuff, but we are trying to set up a boundary condition so you can study it in a very easier way. And then we also assume that linear velocity, meaning that the velocity, as you can see, um, this movement, right, is actually linear. Okay, so let me explain the graph itself. So why cannot go up? Okay, so this is the area. This is the force that push the plate to this direction. I don't know what is U. I think U is the plate of the speed of the plate. And then this is the Uy is the rate of change of the velocity against along the h. Okay, so if h at maybe 0, and therefore the velocity is 0. If it h is 1, and then it's at this point. So this is the rate of change of velocity of the fluid. This is the velocity of the plate. Velocity of the plate, rate of change of the fluid itself. Rate of change of velocity of the fluid. So with this in mind, we assume that the velocity is linear. Okay, what is linear is that the shear stress, okay, the shear stress, as you see, is the stress between the plate surface and the fluid itself. Okay, or maybe this fluid and the fluid over here, there is a certain shear stress, right? There's a friction over here. There's a, maybe I use another color. This is moving in this direction. There's a certain friction over here because there's the the plate itself over here is trying to pull back. Okay, and then the velocity and is proportional to the rate of change of the velocity of the fluid. Okay, so because as you see as you move the plate, as I say earlier, very earlier ago, um, when you push the plate, the fluid over here is so called stick to this surface over here. So when you move, it move. So this place is so called trying to resist. I mean, this place is trying to resist the motion of this. So this friction over here pull this back, and this one pull this back, and then pull this back. I hope you get what I mean. So therefore, they are somewhat proportional. We will assume that this is proportional, and therefore, this is the stress, the shear stress of the fluid is equals to force over area, as you remember. Is proportional to, as we mentioned earlier, is the rate of change of the fluid velocity divided by the small change of h. That means y lah. Okay. So therefore, and then this equation is because I do tutorial already ma, so I would say that this is a very important, very useful equation, and then we need, as you can see, they are proportional. So normally proportional, you need a constant k, right? So the constant k itself is actually the viscosity index. We call it u with a different shape. So there is this type of u, which is the speed of the plate, and this is the u, the velocity of the fluid, and then the very exaggerated curvy u is the viscosity index. Okay, so don't get mixed up when you see a lot of u's. Okay, so there is three rules here. There is three assumptions. So first is the no slip. Okay, I just want to sum it up. Meaning at this point this is 0 compared to here. Okay, this is by far I know, but I don't know the reason behind that. And then why is it? And then no pressure gradient. Okay. Then the third one, no pressure gradient means we assume that there is no pressure low or pressure high at different depths. And then the last one, we assume that we can use this formula when they are proportional, when this trend is proportional. If they are not proportional, it is a very complex system, then we cannot use this formula anymore. So make sure you note it. And then you give me a minute. You may wonder why this page. Okay, this page is just saying the fluid itself, it's follow the Newton's third law, meaning this is the thing, how it flow. Okay, it's just the resistance to the movement of one layer of fluid over another fluid. Okay, one layer of the fluid over another layer of the fluid is just a stress. It's just to the viscosity, meaning it starts to describe this phenomenon. So this is just another point of view for what I think so lah. So nothing much. So you don't worry about that. Just one key thing is this one, you need to understand the graph. I mean this symbols and everything. And then another slight thing I need to convey is before I end this video is kinematic viscosity. Okay, viscosity can also be described with this formula. This is viscosity. Okay, maybe I should cancel this and write it in terms of. So this is viscosity, and this is velocity. So this is the density. Well, like I write my density, velocity, viscosity, or whatever. So density. So as you can see, the viscosity wise, if you were to increase the density. Let's say you bring this up, okay, density times velocity. So if you bring this density up, the viscosity of the fluid itself is partly of the density and partly of the velocity that move it. So therefore, the higher the density, the so-called the larger the viscosity, meaning it flows slower and slower. You know, the fluid flows slower and slower down. Okay, so this is what it means. And in another manner, if density is larger over here because it's at the denominator, so it retards the velocity. So if this one is higher, then this one is the velocity will be lower. So this is the kinematic. Kinematic itself means study of the motion. Okay, that means it's moving, dynamic. Okay, so with this I'll end this part. Okay, and we have a lot of things to talk about over here. And yeah, to see you next video.